We're going to head in a little bit of a different direction for this video and look at universal gravitation, and then we'll tie it back to circular motion. It fits nicely. So to start out with, we'll talk about good old Newton, genius that he was. The famous story of him being in the orchard and being hit by the apple probably didn't happen, but he might have seen an apple fall. And the realization that he had from that experience, or whatever you want to call it, was that the same force that attracted objects on Earth, which tended to pull things always toward the center of the Earth, regardless of which side of the Earth you were on, that was the same force that held the Moon in orbit around the Earth. And so linking some terrestrial objects or properties with celestial properties was kind of a giant leap and was pretty revolutionary. As that realization, he found that the gravitational force between any two objects with mass is proportional to the mass of each object. So if you double the mass of the Moon or the Earth, then the gravitational force between those two things would double. And by looking at how the planets behaved, he was able to figure out that that force decreased with the square of the distance. He didn't know this. Not yet. He knew that there was some proportionality constant, which eventually we found was 6.67 times 10 to the negative 11th. We knew it had to be something pretty small, otherwise a person walking by you, which has mass and you have mass, would exert a significant gravitational force on you. So we knew it had to be pretty small, but the exact measurement of this didn't come in Newton's lifetime. Actually, it came a little while after. It's kind of an interesting story. We wanted to figure this out. Some of them, we wanted to know exactly what that equation was, but some of the motivation was if we knew that gravitational constant, we could figure out the mass of the Earth, which was unknown until that constant was measured. And we'll go into details of how that's figured out later. But in order to measure that gravitational constant, they're like, well, scientists figured we needed a pretty sizable mass, and then we could measure the gravitational force due to that mass, rather than just the gravitational force of the Earth, because we didn't know that mass. So one thing they tried is they figured if they held up a plumb bob, so that's just like a weight on a string that hangs straight down, more or less, and if they were near a mountain, the gravitational force due to that mountain should pull our plumb bob sideways a little bit. So instead of hanging straight down, it would tilt, obviously exaggerated. But if they could measure that tilt, they could then figure out the gravitational constant. They actually chose this mountain in Scotland called Schiehallion because it was pretty symmetric around the mountain, and there weren't a lot of other mountains around it. It was kind of isolated, so they figured that wouldn't mess up the data. And they hired Mason and Dixon, the guys who made the line, to do this surveying. They were surveyors, right? Did the Mason-Dixon line here in the good old US of A. So Mason and Dixon were supposed to survey this mountain and kind of detail all the different levels of elevation and all of this so that they could get a good estimate for the volume of the mountain. They knew approximately the density of the rocks, so with the volume and the density they could figure out the mass, and then with the mass and this deflection and the mass of the plumb bob, they could figure out the gravitational constant. Turns out they weren't able to do it. They just didn't have sensitive enough instruments. But there were some interesting things that came out of this. As Mason and Dixon were trying to figure out the volume of this mountain, that was the first time they ever used lines of equal elevation to kind of delineate different portions of the mountain. So that's where topographical maps came from trying to figure out the mass of the Earth by measuring the gravitational constant. Pretty cool story, huh? That's right. Okay. It was actually, they were successful in measuring this. I think they did in the 1770s, I believe. Anyway, they were successful at measuring the gravitational constant in a laboratory with very small masses. This is the famous Cavendish experiment. And they had some masses on a rod hung by a really thin fiber, and then they held another mass up to it, and that caused this other mass to rotate ever so slightly. In order to be able to see it, what they did is they hooked a mirror And so if this is on a really far away wall over here, they shown a light source on the mirror, and they looked at that light beam hitting the wall, so that any tiny movements in that mirror would be magnified on the wall, and so that enabled them to read these tiny movements. And they knew about the properties of the fiber, so they could convert that tiny movement into a torsional force, and thus figure out the force between the two things. They knew the masses, they knew the distance, and voila, we got our gravitational constant. Pretty exciting stuff. So now we know that if we have an orbiting object, if you're off the surface of the Earth, then the gravitational acceleration will decrease a bit. So up until this point, we always use gravity is equal to mg. That's pretty much true on the surface of the Earth, where we had g was 9.8 meters per second squared, or newtons per kilogram, whichever way you want to look at it. But if you are significantly far from Earth, this is no longer true, and you can't use mg because that's not g anymore. So you have to use the full Newton's universal law of gravitation, gmm over r squared, where you'd plug in the mass of Earth for one of these masses, the mass of the satellite for the other mass, you'd plug in gravitational constant, and then you need to know the distance between the satellite and the center of the Earth. This distance here is between the centers of mass, and T, not C, give me an eraser, centers of mass of the two objects. Centers, here we go. And you got to be a little careful, because some problems will just give you the distance and some will give you the altitude. If they just give you the altitude, you have to make sure and add on the radius of the Earth to get the entire distance between the centers of masses of the two objects. All right. If you have more than one object and you want to calculate the gravitational forces between, I guess, more than two. If it's two, you just plug it in, it's linear. If you have more than that, you just find the gravitational forces between each pair of objects. So in this case, if I wanted to find the gravitational force acting on the moon due to the Earth and the sun, there would be a force of attraction this way, obviously redrawing an arrow that's already there, and there would be a force of attraction that way. And then you would add these two forces, just like you add vector forces, and you would get a net force going this way due to the sun and the Earth pulling on the moon. The moon would also pull back on the sun with an equal force of sun on moon, due to Newton's third law. The moon would pull on the Earth also, force of, that says moon on Earth, it should be Earth on moon. Switch those. And this one here should be moon on Earth, which is actually what's responsible for the tides, right? It's the gravitational force of the moon on the Earth. Okay, as I mentioned earlier, we found gravitational force by doing mg earlier. Now we have a new way, basically both ways to find gravitational force, gmm over r squared. In this case, if we want to find the gravitational acceleration due to the mass of the Earth, we can cancel out the other mass, whatever object it might be. It's going to be the same on both sides of the equation, and that leaves us with this nice expression here that you can use to calculate the gravitational acceleration on the Earth if you know the mass of the Earth and the radius of the Earth, and if you know the gravitational constant. Now this was actually used to solve for the mass of the Earth, as I mentioned earlier, because we could measure the acceleration just by dropping objects and measuring them carefully. We can measure the acceleration due to gravity. We were able to figure out the radius of the Earth, a long time ago. The Greeks figured that out, looking at shadows in wells and whatnot. So this was the calculation we were first able to do when this number was known, to find the mass of the Earth. And we can use this for other planets or stars or whatever. If we can figure out the mass of those objects, which we typically can do by looking at how they orbit other objects, and then if we can get an estimate of the radius, then we can figure out the gravitational accelerations on different planets without having to fly by them and measure them, though we have flown by and measured some as well. All right, quick little example here. What is the effective value of G on the top of Mount Everest? So using that equation we just looked at, gm over r squared, where now we're going to make r a little bit bigger than it typically is and see how that affects the gravitational acceleration on Mount Everest. So this is 6.67 times 10 to the negative 11th. M is the mass of the Earth. That is 5.98 times 10 to the 24th, as I showed you on the previous slide. The radius of the Earth is 6,380 kilometers, so we're going to add 3 more zeros onto that to make it meters. And now we need to add the additional height of Mount Everest, the 8850. That was already in meters, so we don't need to add any more zeros to that, and we need to make sure and square this. This works out to be 9.77 meters per second squared, so slightly less, not a whole lot. That works out to be about 0.3% less than 9.8, so a little bit of reduction, but not huge. Okay, so if you go to Mount Everest, you're not going to be able to like jump really high like you could on the moon or something, but a little bit, though you're probably tired and don't want to jump and don't have any oxygen up there, so not the best idea. All right, now it actually gets a little more complicated than just looking at altitude. Local geology makes a difference. If the bedrock beneath you is more dense than typical, that will actually make a slight difference in the amount of local gravity. So here's some measurements of gravity at different locations around the globe. Varies a little bit, which is one of the reasons why I'm fine with just using 9.8 rather than 9.81 when we're doing our solving problems and whatnot. There's something else I wanted to say about this. Well, I'll remember later. Maybe I'll tell you in class. Okay. This also leads to some interesting things going on with that gravitational acceleration. Oh, I'm going back. I remembered what it was. So I talked to a geologist once. They actually used local gravity quite a bit to identify what's going on in the ground, you know, to find oil and all of these types of things, or what do you call it, geothermal pockets and whatnot. So I was talking to this geologist once. We both had kids on the same soccer team, and I was asking him, how precisely do they measure the gravitational field when they're out, you know, plotting out an area of land? And he said, oh, we can measure to a milligal. And I'm like, what the heck is that? So I went and looked it up. There's actually 1 gal is a unit of acceleration equal to 1 centimeter per second squared. So acceleration is 9.8 meters per second squared, or 980 centimeters per second squared, or 980 gals. And so they can measure out to a milligal. That's pretty dang far, right? That would be like 9.8, and then they're measuring, that would be a gal, and then 3 more for a milligal. They can measure out to that decimal place, and they map areas like that to figure out what is underneath the surface. I think I added 1 too many zeros. Okay, here we go. That one, that'll do. Okay, so if you want to be a geologist, you can use some gravity. Moving on. If we think about the rotation of the Earth and how that affects the gravity that you experience, so altitude plays a role, but the rotation of the Earth plays a role as well. We already saw with circular motion that you need a net force towards the center. Well, if you're on the pole, you're essentially not going in circular motion. I guess you're like spinning on your head or on your feet, so that doesn't matter. So gravity will equal 9.8 there. But here, you need a net force inward. And so what happens, gravity can't change, but the normal force pushing you up actually shrinks a little bit. So it gets a little bit smaller, so you get a net inward force. So on the equator, gravity is slightly less than it is on the poles. You're going to have a bonus problem where you can calculate this. So here, once I got a little excited about it, so this is gravitational acceleration, ignoring elevations and stuff, assuming that the Earth is a perfect sphere, but going from the equator to the North Pole. This is your latitude here, where the angle is in radians. So this is 0 to 90 degrees latitude. Okay, so it starts out below 9.77 and then changes most quickly here at 45 degrees latitude, and then the change kind of levels off and you end up at 9.8 there. The other interesting thing is if you are at 45 degrees here, you know, you've got gravity pulling you down. I'm going to try that again. Whoa, come back. Here we go. Just need an eraser. Just going to try to draw that a little straighter. You guys got nothing better to do than watch me redraw lines, right? All right, so, you gotta be kidding me. All right, towards the center. Come on, line. There we go. And the normal force, if it were outward, even if you made it shorter, that would give you a net force toward the center of the Earth. But if you are moving in a circle like this, you want a net force toward the center of the circle. So not only does the normal force have to shrink a little bit, it also needs to tilt in a little bit. I'm going to make it drastic. So it tilts in a little bit. That way a component of it cancels with gravity, but then you're left with another component of it pushing you toward the center of the Earth. So what this means is if you have a plumb bob, like we already mentioned, it won't be pointing straight down toward the center of the Earth if you're not on the equator or the pole. It will tilt in a little bit. And here again I graphed the angle of the normal force, so degrees of the normal force, that it's off of where it normally would be if the Earth weren't spinning. And this again is the latitude. It's an ugly degree sign, but we'll live with it. And so you get the maximum deflection at 45 degrees latitude, and then the deflection goes away again as you go to the North Pole. So do architects really have to worry about that, the fact that their buildings are crooked because their plumb bobs are crooked? Well, no, because all of the gravitational effects, or the apparent gravitational effects, are all crooked. So the building is not going to fall. If it did fall, it would want to fall in the direction of this force here, right? So all of our building methods are fine and don't need to correct for this. The other thing this does, though, is this is the reason why the Earth is not a perfect sphere. This is obviously exaggerated. That's terribly exaggerated. I can't have it that bad. It's an oblate spheroid, right? So it's fatter on the equator than it is around the poles. The amount by which it is out of round is about 43 kilometers in diameter extra this way. I don't want to insinuate that it's only 43 kilometers in diameter, but it's 43 kilometers, so it's an extra plus 43 kilometers that way than this way. And that leads to some interesting things. We talked about Mount Everest earlier, which a lot of people always talk about as the highest elevation on Earth. That is true, but that's if you're measuring from sea level. But if you are measuring from the center of the Earth, things on the equator will be farther than things off the equator. So it turns out if you're measuring differently, there's a mountain in Ecuador called Chimborazo, and that is the farthest point on Earth from the center of the Earth, or it reaches the furthest amount out into space, which is kind of cool. I actually read, I couldn't find an authoritative source, but it said that even some of the beaches in Peru are higher or farther away from the center of the Earth than Mount Everest, because Mount Everest we saw, well, it's about 5 miles high. This mountain, by the way, is like 10,000 feet less elevation than Mount Everest, but 43 kilometer bulge is pretty significant, and so that lifts things out. This also leads to other kind of strange things to think about. The Mississippi River, which flows south, ends up farther, you know, if it started here, float around this way, ends up farther from the center of the Earth than where it started. But that's okay, because it was still flowing from a point of higher gravitational potential to lower potential, and it all works out. Okay, enough storytelling for today. We'll see you next time.